Hello, everyone. How's everybody doing? I hope you're doing fine. I'm doing a little better, still coughing a little bit, but I'm getting over it. Today, I'd like to talk a little bit about some comments that were made. A couple people came over and they questioned some of what was broadcast last week. It was all about tension. They had a question about tension. And, we grab the bull by the horns here. We do tackle these questions. Someone brings them up, we try to clarify it. Not necessarily for the person who asked them, but other people might have the same question. Say, well, how do you answer this? It's good to get to the bottom of these things. And first thing you have to understand is physics is done with objects. You need to do physics with objects. So, last week I talked about gravity. And if you're going to explain gravity, the mechanism of gravity, you had better propose a physical object as a mediator. Okay, the issue is proposing a mediator. Now, I don't care if you put particles in there. That's fine. I mean, you can say, particles push an object down. You let go of the pen, and particles push it down. That's fine. As long as you're talking about corpuscles, classical particles, we have no problem. We have a problem if you want to introduce quantum particles, because quantum particles ain't particles. Quantum particles are, according to the quantum mechanics, okay, this is not me putting words in their mouth, this is what they say. They say a particle is an excited field. And what is a field? Well, we don't know. It's a mathematical calculation. It's a bunch of values around an object. Could be values for a magnetic field. It could be values for an electric field. It could be values for a gravitational field. They're values. That's all it is. And they're saying these values are vibrating. So that's no good. That's not acceptable. No, if you're going to propose particles, we're talking about real particles, little corpuscles. Make them as small as you want. We don't care, but they have to be objects. Then you can say, yeah, these balls, this shower of little balls push the pen down, and that's why gravity, pushes, toward a particle, a pen or a ball or whatever, a rock, towards the center of the earth. That's acceptable. At least we have something to work with there, right? Space-time, it's out. Why? Because time is a concept. I mean, you might argue all day long that space is a physical object. Let's concede. Time for sure is not a physical object. So you cannot say space-time is a physical object. You cannot say chair plus time plus 1 second or 1 hour is chair time. And chair time is a 4-dimensional object. No way. Time is a concept. And then you cannot say, well, Bill, you're making fun of us, poor relativists, you're not supposed to take the analogy literally. And yes, I do. I'm sorry, I do. Why? Because you're telling me that you're bending space, time, you're bending time. And because you bend time, the Earth goes around this depression that is bent. And that's why it doesn't leave the solar system. So yeah, if you're going to use it as an analogy, we have an irrational analogy because you're saying time is a physical object. That's where your irrationality comes in. And so no, we cannot use space-time. You can use particles, real particles. You cannot use the concept of field and turn that into a particle by saying it's a vibrating field. So we have to clarify that up front. If you're going to do gravity, you can't do it. You need a mediator. If you don't put a mediator, you're going to be doing gravity with magic, with black magic. You're putting spirits in that same space. You cannot say that, for example, that this particle, green one, somehow affects this other one far away, and that there's absolutely nothing in between. Okay? So if this one pulls on this one, or this one shakes and this one forces this one to shake, and you realize they're entangled or whatever, You can't say that there's nothing in between these two balls. Not in physics. In religion, you can, because that's irrationality. So you can say, you're essentially filling the space with spirits, okay? Or magic, black magic, God, or the angels, or the devil, who knows? So, no, you need a mediator for gravity, okay? And I always give an example. People say, well, is there always a mediator? We can't see gravity. We can't see a magnetic field. We can't even touch it. Well, I can touch, I can't see air, but I can touch it. Like, I can't see the air here. But, I take something in. There's some kind of gas, something going inside my mouth here, my nose or whatever. So there's something there. I can't see it, but we know there's something there. And you say, well, yeah, it's air. And we know the air exists because I can touch it with my tongue, with my nose, when I breathe. I can also wave my hand and, I feel something there. But you don't see that with gravity. You can't see or touch it. Or is that true? I mean, when you fall from an airplane, hopefully with a parachute, why are you falling downwards? I mean, you don't see gravity, whatever gravity is, but something is either pulling or pushing you down to the center of the earth. Now, in this case, I don't care if you say, look, there's a whole bunch of particles just pushing me downwards towards the center of the earth. Okay, if you're going to put particles, that's acceptable, at least as a starting point. But you cannot say nothing came in contact with your body. Okay? Cannot say that absolutely nothing touched you. So just like the air that you breathe, gravity touches you. You can't see gravity, but gravity is touching you. It's not touching you in the way you would like. Like with the air, I can wave my hand and say, well, I touched something in there. With gravity, what did I touch? Well, with gravity, for sure, you touch something because something is pulling on you or pushing you. I say it's pull, but I'll even accept those people who say push in this case, right? It's a good starting point, at least, for a discussion. But you cannot say nothing came in contact with your body. Why didn't you fall towards the moon? Why didn't you fall towards the sky and up into space? Something obviously is coming in contact with your body and is touching you in some way or form. Okay? So yeah, gravity does touch you. I have a better example, and that's the magnetic field. What is a field? A field goes around a magnet, right? And we know, or we label it, we say the field is made of all these lines of force. So what are those lines of force? Are they physical entities? Is that something? And a lot of people, especially the mathematicians out there, say, well, those lines of force don't really exist. We use them, to explain what's going on around a magnet. You have a problem with that because the lines of force, why are they called lines of force? Because they have something to do with force. They cause a force on things. Among them, the iron filings that you sprinkle around the magnet. If you put an iron filing close to the magnet, something draws the iron filing to it. Why didn't the iron filing go the other way? No, it was drawn in there. Is there no physical entity that came in contact with the iron filing that somehow has something to do with a magnet? Here I'll show you a little GIF, a little picture here, a little movie. And you'll see that, the iron filings are touched by something. They do come in physical contact with something. And we don't see it when you do it on your desk and you throw a bunch of iron filings around and say, oh, look, how neat. All the iron filings just piled up on the magnet. And pull the magnet up, all the iron filings stick to it. But how about, if you put the magnet underwater? What will it do to the iron filings? And here we see it, okay? Here you'll see what they do. They are collected, the iron filings are collected one at a time. Something is drawing them progressively towards the magnet, one by one. So something is going on there that is coming in contact, in physical contact with the iron filings. Now, if you put your hand there, you won't feel anything. Somehow you're not attracted to the magnet. But the iron filings know better. Something is touching the iron filings that's originating in the magnet. Okay? So yeah, we can touch a magnetic field, in this case indirectly, and we can touch gravity. Because if you fall from an airplane, you get pulled towards the center of the earth. Now, imagine you're a parachutist, you're falling, towards the center of the earth, falling down. Suddenly a gust of wind pushes you upwards. And we're at the bottom, we're looking at you over there. We're saying, oh, how come you went up? Well, we speculate and say, well, it looks like a gust of wind just pushed him upwards. Yeah, but I didn't see anything. I didn't see a gust of wind. I just saw him falling and suddenly he goes up again. Why did he go up? Well, we have to rationalize and we say, well, there was some wind that we can't see. It's some air that pushed him up. Why do you think it would be different to say that, when you fell from the airplane to begin with, why were you pulled down if nothing came in contact with your body? Are there spirits intervening between the earth and you when you parachute, when you fall from an airplane or fall from a mountain or whatever? No, hopefully there is a physical entity that we cannot see. We can obviously touch, at least touch in a specific way. The thing touches us and pulls it down. We can't touch that thing that's pulling us, that's coming in contact with our body. But yeah, hopefully gravity is mediated by some physical object. Okay? And so we started last week with a statement by Professor Richard Muller from Berkeley University. And that's a good place to start because he says, essentially he says, every atom on Earth is pulling on every atom of you. You're also pulling on it. The amazing thing about gravity is that it goes right through things. Now, if every atom in the universe or on Earth is pulling on you and you're pulling on it, right? Well, how does it pull if it doesn't make any physical contact with you? How can an atom pull on, or an atom of the Earth, right, pull on an atom of your body if there's no mediator, no physical mediator? How can it pull? Okay. So yeah, you do need some kind of mediator there. Okay. And so what did I do? Last week I explained my version of it, which essentially mimics or simulates what Richard Muller just said. He says every atom is pulling on you, you're pulling on it. Every atom is interconnected under the rope model, and this is essentially the mechanism. What we have here is the inverse square of the distance feature of gravity. When if every atom of the cylinder is connected to every atom of the cube or the box there, when they're far apart, all the ropes come together and act as one. They pull as one. It's like a single coaxial. And when they get closer and closer and closer, the ropes fan out because every atom is connected to the atom of the other object. Okay, straightforward. I think we don't need to go over that too much in depth. Here, let me put another example why that happens as the cylinder approaches the box. We see that the ropes that connect every one of the atoms fan out. Okay, so each rope tugs independently. Okay, and when I said there is no tugging, there is no pulling. Okay, the ropes simply have tension. Between any two atoms, there's only tension. And that was the issue that was raised by these folks, okay? And let me show you that one more time. All we have is distance between two objects. As they come together, you can see what's happening to the ropes. They just fan out. and that we applied to Newton's formula. We replaced the F for force with a T for tension. We replaced the mass values with actual objects, okay? And we have a distance between the two objects. That distance is not a value, it's not a meter, not a foot, not a centimeter. What it is simply qualitative distance, the separation between the two objects. That's physics. The other part that's physics is the interconnection between the atoms. Okay, that is a physical mechanism that we have there. Okay. Okay, so what was the problem? What was raised by these individuals who came and criticized the idea of tension? The fact that tension, as far as they're concerned, should vary with distance. Essentially, that's what they're saying. And here are their comments, okay? And they're saying, look, according to your model, if two objects start out light years apart and gravity draws them together and then get to be, say, 100 meters apart, the tension of your ropes will be the same as the tension on your ropes if the objects start at zero velocity at 100 meters apart. Okay, yeah. Their speeds towards each other would be dictated by their distance apart. That is the rope tension, and not where they started from. Your ropes are like an anti-spring. A stretch spring starts out with a large amount of tension and loses tension as the spring collapses. Yet your ropes increase tension as they draw together. Another fellow has a similar idea. He says tension should decrease when objects get closer. Why? When they are far, the vertical component of the tension is nearly zero, and the horizontal one is nearly maximum when they are close. The vertical component of the tension is nearly maximum, and the horizontal one is nearly minimum, and all this because of the geometry. Okay, so essentially they have this notion of tension of ordinary experience of everyday life. And here we have a little rubber band, okay? And more or less have it flat here so that you can see what I'm talking about. But you can see that as you stretch it, it gets thinner, okay? The vertical component gets thinner and the horizontal component gets wider, okay? It gets longer, okay? And vice versa. When you put them together, you know, the vertical component gets higher and the horizontal shrinks. So that's what they're talking about, okay? That's essentially the notion they have of tension. And that's not the case with a rope model. And that's why we need to understand the rope model before we can criticize it. You know, first you have to understand the model. And the model says that, you know, there's a single thread in the entire universe that comprises all the matter and the ropes that mediate between matter, which is the matter being the atoms. Okay, so we have the model, which is atoms interconnected by ropes, and all of it, the whole shebang, is made by a single thread floating in the universe. And I propose that it's a closed loop thread. Okay? Now, how it got that way is beyond a discussion today. That's a separate issue. I'm just saying that's the proposal. The proposal is there's a single thread in the entire universe. That's all there is. Now, one of the problems that pops up here is with the term elementary or fundamental. In quantum mechanics, they have a definition known as elementary particle or fundamental particle. What is a fundamental particle? What is an elementary particle? Well, examples are, for example, the electron, the quark, maybe the gluon. You know, these are considered to be elementary or fundamental particles. What do they mean by that? That means that these particles are not made of anything more basic yet. They're not made of anything. Okay, so should we take that at face value and just keep it forever? Well, no, because see, they don't mean what they say. What they're saying is, for now, and from what we can do in the lab, we cannot break that up into further particles. So they're not talking in a conceptual way. They're talking in a pragmatic way in what they can measure or what they can do in the lab. So the term elementary or fundamental particle is meaningless in quantum mechanics. It's a what do you call it? It's a definition that is after the fact. It's what is known as an operational or functional definition, which is an irrational definition for the purposes of science. It's irrational because the person doesn't start by defining the term. He says, let me run an experiment and tell you whether this thing is fundamental or not, whether it's elementary or not. So you say, okay, here's the atom. And the guy says, okay, let me smash the two atoms. So he smashes the atom. He says, is the atom an elementary particle? No, because I smashed it and I got protons and electrons. Okay, so is the electron an elementary particle? Well, let's see. Let me smash it. Give me some money. I'll build a bigger collider. Let me smash it and I'll tell you. So it turns out he eventually gets this money. He gets his collider. He smashes two electrons and he manages to break them up. And now he says, well, you know, an electron is made out of tonies. So now we have electrons made out of tonies. And what is tony made of? Well, it's an elementary particle, so it's not made of anything. Well, give me some more money. I'll bring a bigger collider, and I'll tell you what it's made of. And so on, they go on and on and on, and they never reach an end. But it turns out that quantum mechanics predicts, to use their famous term, predicts that there should be an elementary or fundamental particle that constitutes everything else. How is it that I know this? Well, you can smash a particle, break it apart as many pieces as you want. You'll never end up with nothing. You will always, at the end of the yellow brick road, you'll always end up at the end of the road with something. That something is your famous elementary or fundamental particle that constitutes everything else. And you cannot say, well, what is it made of? You can't ask that question because by definition, it's an elementary fundamental particle. That means it's not made of anything smaller, of parts. And quantum mechanics doesn't pay attention to their definition. They say, well, let me see, I'll collide it in the collider and I'll tell you what it's made out of. See, under the rote model, we start out with rigid definitions. And when we say that the thread, because some people ask, what is a rope made out of? And it's a very offensive question because it means they haven't even taken the trouble to understand the basics. And I always give them a snide comment. I say, it's easy. Rope is made out of two strands. I mean, it's obvious, right? You have two twined strands. What part didn't you understand? Because the question they really want to ask, and they're not paying attention to what they're asking, is not what is the rope made out of. What they want to ask is what is the thread made out of. And if they can't tell the difference between a thread and a rope, they got a serious problem. So yeah, I usually treat people who ask, what is the rope made of? Oh, I love that question because I'll I'll treat them in a way that they will not like very much because it's the wrong question. It means they're not even thinking of what they're asking. So what is the thread? Well, the thread is an elementary or fundamental entity. Does that mean I'm going to take it to the collider, smash it, and tell you what it's made out of? No, it's a conceptual issue. I'm saying that the thread is an elementary fundamental entity. That means it's not made of anything because it's the thing that makes everything else. The buck stops there. Okay, so the thread is a fundamental elementary entity, and what that means, it's not made of parts. It's not made of anything smaller. It's a single piece entity. What does that mean? It means it cannot stretch. See, this guy stretches. Okay? Think of the same thing, but it cannot stretch because it's made of a single piece. And yeah, I know people are going to say, well, it's flexible. I'm not going to get into all that little detail right now. Not today. That's not the point. The point I'm trying to make is we use the definitions and we stay by those definitions. Definitions are ground in stone. We don't alter them at our convenience like in quantum mechanics. Oh, what is an elementary particle? Well, it's a particle that's elementary until I can break it into pieces. Until then, it's tentatively an elementary or fundamental particle. Not so under the rope model. In the rope model, when we say elementary entity, it means it's not made forever and ever. It's not made of anything smaller. It's made of a single piece. Okay? And if it's made out of a single piece, you can't stretch it because otherwise you would be creating matter from the void. I mean, if in this case it's just a question of structure, right? I haven't created matter. But imagine the fundamental entity, the thread. If I could stretch it, well, where's the extra matter coming from if it's made out of a single piece? If I can stretch it, I'm creating matter from the void. That's why I postulated that the single thread is made out of a single piece and it cannot be stretched. Okay? Why is that important? Well, it gets back to the issue of tension. See, now you can't do this with a thread. Okay? You can't stretch it and it becomes thinner and then it becomes fatter and so on. You can't do that with a thread because it's made out of a single piece. So it doesn't stretch. Okay? So here's the single thread universe that I'm proposing. Okay? Here we'll start in a second. Give it a second here. So we start at the beginning. I'll drink my mate meanwhile. Here it goes. That's the single thread universe. What does it do? It twines around, okay, and creates the rope. And what does the rope do? It ties any two atoms, which I'll go in a minute. But then all the atoms in the universe are interconnected by these ropes, and they are made of these threads. Okay, the same thread that makes the ropes, the same threads also constitute the atom, especially the hydrogen atom, which is the one we're concerned with here, which is 90% of the universe, of the matter in the universe. Okay, so where does that lead us? Well, it leads us to the construction of the atom. We want to understand how the atom is constructed with these threads. And again, we have a single thread. I color code one versus the other, and I call one the electric thread and the magnetic thread just to distinguish them so that we can relate it to the electromagnetic wave. So I'm just being consistent with tradition. That's all it is. It's convention. That's all it is. Okay. So some people ask me, why is one electric, why the other magnetic? No, it's a single thread in the entire universe. But here's the construction. If you pay attention to the construction, you'll see how the atom is constructed under the rope model. Okay. Doesn't mean you're going to believe it. It just means that I just hope you understand it. Okay. Here it goes. Okay, let it start in a second here. Okay, so we have the electric thread goes straight through the center of the atom, and the magnetic thread coils around and encapsulates all the electric threads from every atom in the universe. Okay, that's the proposal. Okay, electron shell made from all the magnetic threads of every atom in the universe. What we have is the atom there. You can see the little star in the center. That's the proton. And here it is a little bigger so that you can see it in a little more detail. You see the ropes end at the red line, which is the electron shell. Okay? That's in a nutshell the system. Not too complicated. I think this is for anyone who has a mentality at least of kindergarten and above, you can understand this. Hopefully, you know what I'm trying to propose here. It doesn't mean you believe it, it just means you understand it. Okay? Okay, so that's the construction of the rope. Okay? Now, what is our basic system? Well, let's assume that dear old God or Father Universe or Mother Nature, whoever you believe in, you know, creates just two atoms. That's the minimum system. Okay? And this is what they would look like. Okay? We have there, you know, two atoms connected by a rope. That's the basic system. Okay, and let's assume that Mother Nature, Father Universe, whoever, just created two atoms in one rope. So that's the entire system right now. Okay, and are these if these two atoms can I pull them apart and stretch them? Well, the answer is no, I can't. And if I put them closer together for whatever reason, okay, the question is what happens to that rope? Okay, and that's a special situation. I'm not going to discuss that one right now. I'm just going to say that if you take them apart, you cannot, because there's only so much matter in that whole system. That same rope is the one that is going to constitute the atoms, and here I'm showing more threads than I should in the case of the atoms, because I'm showing a bunch of threads from every atom in the universe, a bunch of threads forming both the proton and the electron shell. But if we only had one, like I showed a minute ago here in this here in the construction, let me show that one more time. Here you can see a single thread. So that's what essentially we would have. We would have only a single thread and a single rope. Okay, that would be the cross section of an atom. Okay, and the question is, can an atom, run away from the other? Well, if they both weigh the same thing, they have the same mass, and we have a single thread there in the whole thing, well, no, that thread is not stretchable. Okay, and I showed that the other day with this little illustration here. We have two atoms made of a single piece. Each one of those is made of a single piece. You have something interconnecting them. We'll call it a thread, wire, whatever you want to call that. And that thing is made out of a single piece. And no one wins that tug of war. There's tension, but there's no increase in the width or the length of that intermediator. Okay. So because the rope doesn't stretch, the threads don't stretch, then no, the tension always remains. It's always the same tension, no matter how far apart they are, how close they are. That rope will not gain or lose tension. And there's another issue that just reinforces that. You should be aware of it, at least if you're going to try to understand the rope model. And that's the fact that the velocity of light is constant throughout the universe. And what they've done in mathematical physics, they created the refractive index table. You want to know how fast light goes through glass? Well, you got to divide the velocity of light in a vacuum, 300,000 kilometers per second, divided 1.45, which is approximately, there's different kinds of glasses, but that's the typical one, 1.45. So you get like 200,000 kilometers per second, somewhere around there. And the issue is that the speed of light in glass? Is that why we have that breakage? Like when you put the pencil in water, it breaks, that refractive break that you see in water. Is that because it goes from air to water? Is it going from less dense medium into a more dense medium? Is this like swimming in a lake and then you swim into molasses, so you go slower, and then you swim into mud and you go even slower? Is that how light operates in real life? It just goes slower depending on the density of the medium? Well, not under the rope model. Under the rope model, it's very simple. Light always, always, always travels at 300,000 kilometers per second between any two atoms in the universe. It doesn't matter if the atom is part of a solid, a liquid, a gas. And people say, well, that's counterintuitive. Well, what is counterintuitive is the Ptolemaic system, where you have to change speeds of light depending on the medium through which it traverses. And so, no, light always travels at the same speed between any two atoms. Why? Because what changes is there's an exchange between frequency and wavelength. Okay, we have the equation for that. So there should be no mystery, and it never sunk into the minds of these people, because they've always dealt with one-way systems, with waves, transverse waves, and particles. But when you look at the equation, you can see why that's an equation of a rope. Okay, it's c, velocity of light, right? 300,000 kilometers per second is equal to frequency times wavelength. If you raise the frequency, you must lower the wavelength and vice versa. Okay, so you cannot have a different speed for the velocity of light because it's a constant. But they say that little c is only applicable to outer space, to vacuum. But it turns out then they fill the vacuum with all kinds of garbage. They say, look, the vacuum is made or filled with all kinds of stuff. They don't call it the ether, but that's what they're referring to. They're saying, look, the vacuum is or is filled with particles. They're virtual particles, particles that pop in from space out of nowhere. They just kind of form themselves at the last moment. Or they say that's vibrating fields or excited fields, or they say it's a bundle of energy, or whatever. They say there's all this vibrating energy, all these excited fields, all these virtual particles that comprise the vacuum space or that fill the vacuum space. Okay, and so the question is, if light has to travel through all that garbage, right, especially when they pop in from the void and then go back in, well, light should travel at different speeds every second. There shouldn't be a constant velocity of light with so much garbage that gets in the way of the velocity of light. So yeah, it's counterintuitive is the opposite. It's the Ptolemaic system that they created known as refractive index, where you have to change the speed of light through every medium light goes through. And here you can see why under the rope model it's very simple, very straightforward. Velocity of light is always constant. Why? Because what changes is the frequency in exchange for the wavelength. If you increase the size of the link, if you make it longer, you're going to have fewer links for the same amount of rope. And that is the difference between, higher frequency and lower frequency, or greater wavelength and lower wavelength. One is in exchange of the other, because under the quantum version, there is no reason for you to increase both. You should be able to increase frequency and wavelength and travel faster than light. And that's not possible under the rope model. Okay? But see, they never explain that. They say, well, can we travel faster than light? And they say, no, we can't. Well, why not? Well, they can't tell you through the equation. Right there, they forget about the equation. They say, well, you can't because it would turn into energy according to another equation, which is energy equals mass times velocity of light squared, E equals mc squared. And so they use that equation. But how about this equation? I mean, this is an older equation, C equals frequency times wavelength. And they don't deal with this equation. You'll rarely see anyone analyze that to any great depth, because it's straightforward. The velocity of light is 300,000 kilometers, and it's known to be a constant where the only variables are frequency and wavelength. Okay, so you figure it out. Anyways, the issue is that, yeah, if the velocity of light is 300,000 kilometers per second, it's always a constant. It's a measure of the tension between any two atoms. It's a measure of tension on a rope. It's constant. The rope doesn't stretch. You don't create matter from the void with a rope. Whenever you, I don't want to get into too much detail, but whenever an atom goes through a rope, because it also eats rope, and like, a little bead going through the abacus, and it releases rope behind, and it reels in from front and releases in the back as it travels along a rope. Okay, it slides along a rope, and it's pumping and it's shaking. It's got all these motions, and we have to analyze each one of these. We got to explain the Mossbauer effect, the fact that there's no recoiling of the atom. There's many things to explain, and you have to explain each one of them. And for that, you need to really analyze the rope in detail, so that you don't ask the wrong questions. Okay, once you analyze each one of these situations, each one of these phenomena, then you get a better feel for the rope. You say, okay, the rope can explain this, the rope can explain that, etc. And yeah, the point here is that the tension on the rope is always the same, no matter where, between any two atoms. Why? Because the velocity of light is a measure of the tension of the rope, and the velocity of light is a constant. It's always 300,000 kilometers per second. Why? Because the equation says that velocity of light, 300,000 kilometers per second, is equal to these two variables, frequency and wavelength. One changes at the expense of the other. What do you get when you have longer wavelength, shorter wavelength? You have difference in colors. What do you get with higher frequency and lower frequency? You get the amount of energy, how much energy light has, okay? And that's a can of worms, a big monster, but you get an idea where I'm going with all this. The point here is, what we have is constancy of the speed of light. That tells you that the tension is always the same. Why? Because when you look at the original proposal, the fundamental proposal is that the thread is an elementary entity, elementary medium. Okay? Elementary means it's not made of parts, it doesn't stretch, there's a single thread in the entire universe. So that's the proposal. Whether you like it or not, I'm just saying, this is the proposal. Okay, we start out there and we say, look, because it's not made of little parts and because it cannot create new matter by stretching, the tension has always has to be constant. And that's also dictated by the constancy of the velocity of light. So it all matches. It's a self-contained system. It's a comprehensive system. Okay? You don't have to guess why light travels at a certain speed, why it's so fast, why frequency is inversely proportional to wavelength. The rope tells you all that. Okay? Just by looking at it, just by visualizing it, you understand all those issues. Try to do it with quantum. Good luck. Okay? So the other thing we need to mention about gravity is that weight is location dependent. Weight is a static concept. People don't always understand that very well. See, weight, according to Newton's equation, is a force. Force equals big G, right? Mass divided by distance squared. And you do the calculation, say, well, that's the weight. But what have you calculated? You calculated the distance between two objects. Is that distance, you're going to unroll the measuring tape? No. Mother Nature doesn't know anything about meters and feet and yards and so on. Mother Nature just sees separation, gap. Okay? And what's she really seeing there that you can't see? The interconnections between the atoms. Closer they are together, distance is shorter. Okay? Now you have greater acceleration. But acceleration, in order to see the acceleration of gravity, you need to run Newton's equation many times. If you only get one solution, just one solution, for Newton's equation, force equals mass divided by distance squared. Let's forget about the G for now, it's a constant. Mass, distance squared. All you have is two objects separated by distance. You're talking about a static scenario. You're saying that weight depends on that distance, on that separation. What happens when you move closer to the other object? What happens when you move closer to the bathroom scale? Well, you weigh more. That's what it is. You press down harder, you're going to weigh more. Yeah, that little, meter gauge is going to read higher. So we have to understand what's happening here. If you're in outer space, you're an astronaut. Let's say you could maintain a certain orbit. Okay, you're 100,000 kilometers away from the Earth, and you're going around the Earth. You take one step forward towards the Earth, 100,000 kilometers minus 1 kilometer, you already weigh more. You weigh more simply because of your location. You changed your weight You could say instantaneously. In other words, by changing your location, okay, you change your weight. Because weight is, according to Newton's equation, mass divided by distance square. Distance determines how, the two masses are the same. Nothing has changed. You still have 100 kilograms here and 90 kilograms here. Nothing has changed. All you did is position them closer to each other. So it's distance. And just by getting it closer, the distance square factor, you change the value of the force, Newton's force, actually tension. Okay, and all you get is one value every time you find a solution to force. You can only get one value at a time. Only when you plot that do you get acceleration. But for every single solution, all you have is one weight, one distance. I hope I'm getting through with all this to you, okay? You have to understand the physics of it, okay? And so here's a little picture that I made. Here's a box falling to earth, okay? That's typically how you would see a box falling to earth. It somewhat accelerates, okay? I try to mimic it as well as possible, okay? And you can see as it falls, it accelerates, okay? That's how a box falls to earth. It falls at 9.8 meters per second square. What does that mean? It means it increases its velocity 9.8 meters per second for every second. So every second that passes, you're increasing the velocity by 9.8 meters per second. That's what it means. That's why it goes faster and faster and faster. How do we explain this physically? Well, under the rope model, it's kind of quite straightforward. We have all the threads that we can't see. Mother Nature can see them, but we can't. And that's what's tied to you when you fall from an airplane. Okay, you fall from an airplane, what's in contact with you, this gravity, this invisible gravity, just think of those as every atom in your body connected, physically connected to every atom on Earth. There you see the angles are different, okay? And that's why you fall faster and faster and faster, because as you approach the Earth, the ropes that connect every atom in your body to every atom on Earth, they fan out. That's why you fall with increasing speed every second. That's the acceleration of gravity right there. So we have a mechanism. Now, again, whether you believe it or not, that's a separate issue. I'm just telling you I have a mechanism that you can visualize here, okay? And just to show you one more thing here, it's different if you jump on your scale. You know, you're going to weigh a lot more if you jump on your bathroom scale. And you say, well, hold it. If a hydrogen atom is at a given location from the Earth, let's say 1 kilometer, or let's say 1,000 kilometers, okay? You're 1,000 kilometers away from the Earth. That's a hydrogen atom. And you're away, let's assume the Earth is perfectly spherical, or that you're exactly equidistant from the center of gravity. Okay, so that's a scenario. You have a hydrogen atom, and that hydrogen atom, 1,000 kilometers away from the Earth, has the same number of ropes connected to it, to the Earth, effective ropes, acting directly, as any other atom that is also 1,000 kilometers from the Earth. Okay? But what happens when you drop that hydrogen atom? What if that hydrogen atom is falling, say, from the moon? So it's already got some speed because it's coming towards the Earth, and just at the moment that it hits 1,000 kilometers, it's got a speed, whereas the other atom which you were holding onto has zero speed, it has zero velocity. So one has, I don't know, whatever velocity is greater than zero, and this one has zero velocity. So we're not talking about weight anymore. Now we're talking about velocity. That's a separate issue, and now we have to apply the force equals mass times acceleration equation, Newton's second law. Okay, you're talking about velocity. If on the other hand you want to talk about weight, you talk about how many ropes are connected to your atom at a given distance. Okay, so just be aware that we have to separate velocity from weight. Okay, people are not always tuned into that. They mix as you saw in the question there. You said, hold it, you've got this one that's standing still and the other one that's coming down. When they reach a certain distance from the Earth, they're both connected by the same number of ropes, but this one's falling faster. Yeah, it's falling faster. It doesn't weigh differently, okay, because it's got the same number of ropes at that distance connected to it. In other words, the same effective ropes, independent ropes. But you're talking about velocity, and now you got to apply the other equation. Just be aware of that, because not everybody is always tuned into that. Okay, one more thing that I wanted to mention. Let's see if I can get to it real quick. I'll try to finish as much as possible on this. And this is another fellow who put in there, he wants to insist on the ether. And he says, light is just a vibration in the ether medium. The medium is dipolar, electrons and positron pairs, particles that repel each other. Matter is a crystalline structure of photons. Ether medium particles squeeze into a crystalline structure. Quantum ether is a mathematical. With predictive power, it cannot have material existence. No kidding. So if the ether is not material, I don't know what kind of physics we're doing here. Gravity is the movement of these medium particles towards the low pressure area created by constriction in the medium flowing around and created by matter. Well, I don't know what all that means. I'm just going to address the ether because that's what we're concerned. He says it's the vibration of the ether medium. And anyone using ether is really, in this day and age, it's got a serious mental problem. That's the reality of it. You can't use the ether anymore. Okay? And the reason is here, and I explained it in a few of my latest, if you go through it, you'll find some information. But here, let's see if I can synthesize it one more time. Okay? Here's what this guy is proposing. He's saying, look, that's light. Light is the vibration of the ether medium. So he sees some kind of vibration, that wiggly worm that you see there. And what is that wiggly worm? Well, it's just the vibration of all those particles. That's what it is. They're moving up and down. They're causing this wiggling. And he says that's what light is. That's what a lot of people out there think light is. The vibration of the ether. Okay? So that's the starting point. But we have to go one step back because these people are already moving ahead into theory, and we're not interested in the theory. We want to get to the bottom of the ether. We want to know what this ether stuff is. So that's where we have to start. We haven't finished with the ether, and you can't even start your theory until we cover every base on the ether. Okay, so let's go with the ether here. This is the ether this person is proposing. He's saying it's made of protons and electrons. Okay, that's essentially the ether he's proposing. Positrons and electrons, etc. Okay, so the red ones are the positrons, the white ones are the electrons. You want it in reverse? Okay, we'll make it in reverse. We'll make the electrons red and the positrons white. What are positrons? What are electrons? What is the black stuff that contours each one of these little balls? Assuming these are little balls, that's what I'm assuming. I'm assuming that when the person says electron, he's thinking about a tiny little bead, or we're going to think of it as a round one because that's convenient, only because of that. So what contours that ball? What contours the red and white balls there? Okay, and you can have an infinite ether. Here's the same thing, but infinite and irrespective. We need to know what that black stuff is. We want to know what is that black stuff that gives shape to each one of those particles. Okay, and here is let's zoom in with our microscope and find out what this looks like. And here you see what it looks like. Okay, we have the electron particle and the positron particle. Okay, one is red, the other one is white. Okay, and well, that's one difference. Maybe the color code them. Maybe you want them blue. Okay, fine. And then the other thing is one carries a negative sign above its head and the other one a positive sign. Now, how do these two things attract each other? I mean, physically. Does the plus sign get somehow tangled with the negative sign? Is that how the attraction occurs between these two particles? In other words, we got several issues here. We have first the issue of what's the black stuff? I need to know what's contouring each one of those two particles. The second issue is, okay, even if we concede that, how does one particle attract the other? Are we just going to use the magic wand and say, well, they do, and positive attracts negative? Well, what does positive mean in physical terms? What does negative mean in physical terms? Unless you can put this in physical terms, that plus and minus are absolutely nothing. They're just descriptions. You're saying, well, whenever we have, a particle attract another, we'll call this one the positive one and that one the negative one. And by definition, the positive one is the positron and the other one is the electron. We're done. That's only a description. That's labeling. You still haven't told me the mechanism. Okay? So I need to know the mechanism. And so what I do is just put out a set of questions that anyone who proposes the famous ether has to answer. Okay, these are the questions, okay? Unless you can answer these questions, your ether is worth caca, okay? Does the ether fill space, or is the ether equal to space? In other words, are space and ether synonyms, the same, equal, etc.? What encapsulates each particle that constitutes the ether? In other words, what's that black stuff? If space contours each particle of ether, what is space? Define or draw space. I need for you to give me a definition of the word space, or if you think it's an object, I want you to draw it. And in which case, is space infinite or finite? Well, if it's finite, meaning it's an object, you got to tell me what encapsulates space. And if it's infinite, well, what do you mean by infinite? What do you mean that space is infinite? What does that mean? Is space a physical object that is infinite? And then the last one, is the ether within an infinite space, infinite or finite? Because space, you can say maybe you manage to defend the fact that it's infinite, okay? And then the question is, the ether within that space, finite or infinite? I mean, do we have this situation? Let's see if I get it back again. This one here. See, there's space, we're going to assume it's infinite. And the ether, which is that the red and white balls, the body there, is that finite? It stops somewhere and then space continues to infinity, whatever infinity is. And if space is not infinite, well, what contours space? What encapsulates space? So those are the questions that the proponent of ether has to answer before they rant about their theories. We don't want to hear your theories. Okay? We don't want to hear your theories because they're bunk unless you can get through the qualitative assumptions that you need to start your theory. You need to finish with the ether. You haven't finished with your theory. Spend 2 years on the ether, 1 second on your theory, okay? It's the other way around. You want to talk about your theory, how the ether vibrates, and we proved it in the lab. We don't want to hear any of that. We want to know what the ether is before you start. We're going to bombard you with questions on what the ether is, what contours each particle, is space infinite? Those are the questions we want answered. Okay, and I'm going to answer some of those questions next time around. I'm going to go into what is nothing. What is this? Well, ether. The famous ether. Is space filled with ether? Is space the same thing as ether? And again, I don't think you can vouch for space being equal to ether. And some people say it's both, because they don't understand the question. They're not intelligent enough to understand the question. That's scary. The question is, as I just put them there, you can go back and look at the little chart there. And the important question is, what encapsulates each ether bead? Okay, so if the ether you say is positrons and electrons or virtual particles, whatever you want to call it, I don't care. What contours each particle? That's what I want to know. Okay, that's what you need to specify. If you say space, then space is different than the ether. Now let's deal with space. Is space infinite? What is space? You got to answer those questions. And I'll continue with that train of thought next time, which I think is this coming Sunday. Okay, so we'll see you then. Bye-bye.